Okay, then it's going.
Okay, perfect. Well, I'm going to talk on nonparametric estimation of the directional highest density regions. This is a joint work with Rosa Maria Crujeiras. And before presenting this definition in the directional setting, I will talk a little bit on set estimation theory. Usually, this theory considers the problem of reconstruction some sets of interest, but in the Euclidean space. This theory is characterized by using two important mathematical tools: geometric shape assumptions on the set to be estimated, and distances between sets. So one of the most common problems to be considered in this context is the problem of super reconstruction. We want to reconstruct, in this case, the support of a distribution. I show you an example using the RLC here. Then I will talk on the non-parametric plugin estimation of highest density region. This is another common problem in set estimation. Here I will use a real data set on leukemia to illustrate the problem. Finally, I will extend the definition of highest density region from the Euclidean space to the directional setting. Here, Rosa and I have proposed a new bandwidth selector for the kernel density estimator, because here the goal is not to reconstruct the density function. Here the goal is to reconstruct a set, a highest density region. And I will illustrate this problem with two real data sets. I will use the orientation of some hoppers on the circle, and I will use the distribution of earthquakes in the sphere. So, as I told previously, superestimation is a classical problem in set estimation, and the main task here is, given a random sample of points, to estimate, to reconstruct the support of a distribution. Here I show you the geographical location of the RLC, and from this image we are able to generate a uniform sample of points on the RLC. So the question to solve is the next: is possible, given this random sample of points, to reconstruct the boundary of the RLC? Well, there are two possibilities in literature. Maybe we have as only information source the sample points. Then, in this case, the most natural choice to reconstruct the support of a distribution is use the de Broglie-Weiss estimator. But sometimes maybe we know some shape properties that the support can verify. Maybe we know that our support is convex, or maybe we know the number of connected components that our support has. So there are another more sophisticated estimators in these cases. Well, the first situation: we have only the sample points as information source. So here I show you the de Broglie-Weiss estimator using the previous sample on the RLC. And you can see that this estimator is a union of balls with centers at sample points, and the radius must be selected by the practitioner. So in these figures, I show you three possible selections of the radius. And as you can see, if I select very small values of the radius of balls in A, I have a very fragmented estimator. But if I choose a very high value for the radius of the balls, then I will overestimate the RLC. So this is an interesting question to be into account. So how to select this smoothing parameter? The radius of these balls can be seen as a shape index, and this problem was already considered in literature. Well, the second situation: as I told previously, maybe we know that our support is convex. So in this case, the most natural choice to reconstruct the support of a distribution is to calculate the convex hull of the sample points. So here I show you this reconstruction for the RLC. As you can see, in this case, this geometric property is very restrictive, and another more flexible should be considered. For instance, R convexity. R convexity is a shape property that offers the possibility of considering several different connected components. So this property was studied in these two papers. The first one considered the case as in the RLC when the sample has a uniform distribution in the Euclidean space, and the second one considered the case when the distribution of the sample points is more general. Well, in this point, it's convenient to measure the error. How to know if our estimator of the support is a good estimator? Well, in set estimation theory, it's very common to use distances between sets to measure the error between the theoretical set to be estimated and the corresponding reconstruction. So here I show you the definition of a classical distance, the Hausdorff distance, and I show you this distance in this figure. For the particular case of the RLC, I show you here the Hausdorff distance between the boundaries of the RLC and the convex hull. As you can see here, this distance is high, so we can detect that this is not a good estimator for our support. Of course, another distances could be considered. Well, sometimes the goal is not to reconstruct the support of the distribution in the Euclidean space, because we are only interested in knowing the hot spots of the distribution or knowing the modes of the distribution. So this is the case on this example that I will show you here. So I have a real data set on the northwest of England. I have in B a sample of cases of leukemia, and in C I have a sample of controls. So the question is to know if the distribution of cases and controls is or not similar, or by the contrary, the modes of cases are located in a different geographical area than controls. Well, this question can be solved using set estimation, and in particular, highest density estimation regions. How? Well, first, we will define the concept of highest density region. So given a random sample of points of a random vector X with values in the Euclidean space, a T-level set is defined as follows: as the set where the density function takes values bigger than a level T. This definition is not useful for practical purposes because this level T is usually unknown, and we prefer to consider an alternative definition where the practitioner fixes the probability content 1 minus tau of the level set. So this is the definition of highest density region. Is the level set where the density function f is bigger than a threshold f tau, and this threshold is defined to satisfy this probability content. For this one-dimensional density, I show you here the highest density regions for different values of this parameter tau. If I select a value of tau close to 0, then I will have practically the support of the distribution. Then we can move on to the first problem on this presentation. But if I select big values of the parameter tau, values close to 1, then I will have the biggest modes of the distribution. And this question is interesting in many practical applications. So how to estimate these highest density regions? Well, as in the support case, we have again two possibilities. Maybe we have not more information than sample points, then we will use plugin methodology. I will focus only in this possibility. And maybe we know some geometric information on the highest density region to be reconstructed. So here there are more sophisticated alternatives that will not be considered here in this talk. Well, plugin methods are maybe the most natural and simple choice to reconstruct a highest density region, because if you remember the definition of the theoretical set L2, only replace the density function f by a non-parametric estimator of the density, the kernel 1, and replace the threshold f2 by a non-parametric estimator of it. How to compute this threshold? Well, using the method proposed by Hickman in 1996. He estimates this threshold as the top quantile of the empirical distribution of the kernel density function evaluated on the sample points. Of course, here appears the problem of selecting the bandwidth parameter or matrix, because the goal here is not to reconstruct a kernel, a density function. The goal here is to reconstruct a set. So in this setting, in the Euclidean space, there exist several selectors of the bandwidth. For instance, this one, Sangoran one, proposed the first one in 2010. But in the directional setting, there is no proposal in this sense. Well, for the cases, for the sample of cases and controls of leukemia, I have estimated the plugin highest density regions in the Euclidean space for different values of the parameter tau. So here I have a very small value of the parameter tau. You can see that I have practically the support of the distribution. If I change the value of the parameter tau, I will estimate the modes. And if I select tau equal to 0.95, I can see that the population is concentrated in the south of the map, but the cases of leukemia are in the north of the map. This area is a metropolitan area with high levels of pollution and many industrial factories that maybe could be related to this high incidence of the illness in this part of the country. Well, these problems make sense when our data are not in the Euclidean space, if our data are on the circle or on the sphere. So here I show you a real example on Sandhoper's orientation. We have the angles of Sandhoper's measures in a Tunisian beach. We have two species of sandhoppers, Brito and Saltator, and some other variables such as the moment of the day when the measures were taken, the month of the year, the sex of these sandhoppers. So the question here is to know if, for instance, the month of the year plays a significant role in sandhoppers' behavior. So in this figure, I show you the angles for the species Saltator when these angles were measured in noon, but in April and October, respectively. So as you can see here, we have two clusters in the right picture around angle P, but this not happen in the first figure. So if we are able to estimate here highest density region, we can identify perfectly the clusters of the two distributions and analyze the difference between these two situations. Well, another interesting problem is the next one. Here I show you the distribution of earthquakes on the Earth. Well, maybe an interesting question as an illustrative problem is to know which areas are especially risky. So this problem can be again solved from the perspective of highest density regions estimation. Well, then it's necessary to extend the definition of highest density regions to the unit sphere. So here we have again a random sample of points, in this case of a random vector y with values in the unit sphere, and we define the t-level set as the set of points in the unit sphere where the directional density is bigger than a level t. As before, we prefer to fix the probability content of the level set instead of giving a level t, so we define the highest density region in this way as the level set. Well, now we have a threshold g tau that guarantees the probability content of at least 1 minus tau. Well, here I show you the highest density regions for three circular densities and three different values of the parameter tau. As you can see in the third figure, for this value of tau equal to 0.8, we are not able to detect this mode in the distribution. It will be necessary to consider a smaller value of tau to detect this cluster. Well, here I show you some spherical densities and the representation of the highest density regions, again, for different values of the parameter tau. Here, in the first case, we have a bimodal density, and the last two ones models are trimodal densities. Well, extending the plugin estimation in the Euclidean space to the directional setting, we propose to estimate the highest density region in this way. We replace only the directional density G by Gn, a kernel density estimator, and the threshold by a corresponding estimator. This threshold can be computed again using the method proposed by Hickman in 1996 and as in the Euclidean space, no problem. Again, appears in this case the problem of selecting the bandwidth parameter, and as I told previously, this problem was not considered in this setting. So then I will show you a proposal for selecting this bandwidth in the directional setting. Well, as an example, for the previous circular densities, I show you the estimation of highest density regions from a random sample of points of size 250. As you can see in the third model, we are not able to detect these third cluster. Maybe we need here more sample size to detect it. Additionally, I show you also the estimations for the spherical models for, in this case, tau equal to 0.5. And finally, I show you our proposal for selecting the bandwidth parameter. So here the goal is estimate a highest density region. So sorry. We will like to minimize the Hausdorff distance between the theoretical highest density region and the corresponding estimator. Concretely, the Hausdorff distance between their boundaries. However, this expression is not known, so we propose to estimate it using a bootstrap procedure, generating random samples from the directional kernel GM. Well, the performance of this bandwidth selector was analyzed in an extensive simulation study in this paper in the circular and spherical settings, and we check that in general this selector is competitive. Well, to finish this presentation, I will apply the highest density regions estimation to the problem of sandhoppers and earthquakes. So here I show you the highest density region estimated using plugin methods for the species saltator for 2 months, again, April and October. So as you can see, there exists clear difference between two sets. Here we have a cluster around P, but this cluster or mode does not appear in October. Similar situation occurs if we consider the Brito species, and we consider again the two different moments of the year to take measures. Well, in the case of the earthquakes, we have estimated the highest density regions for different values of the parameter tau. In dark blue color appears the contour of the highest density region for tau equal to 0.9. So the more risky area is the southeast of Europe. But the consideration of the rest of highest density regions for different values of the parameter tau give an idea of the distribution of the earthquakes around the world. And finally, we are trying to create a new R package, including these tools and some additional ones. These are two scatter plots in the circular and spherical settings. And additionally, we are trying to prove that it's possible to estimate the number of clustered or connected components in a consistent way from the plugin estimators. Thank you for your attention.
Thank you very much, Paula, for this very insightful presentation. We do have, of course, time for questions. So I'll also put the video back on. I'm turning towards the audience. Who has questions for Paula? You can raise hands, unmute yourself, whatever you prefer, whatever is most. So you have a nice comment from Giovanni Porzio. Really interesting. I'll go through your papers for sure.
May I ask one question, please?
Yes, please, go ahead.
Hi, thank you for the talk. It was really interesting and insightful for me. My questions would be, these highest density regions are based on the independence assumptions. Do they, in Euclidean space, do they exist some methods to do it for lightly dependent data or something like that? Or in second question, I know it's a hard question. Second question is, does there exist a way to maybe formalize when you compare these highest density regions for two samples, like for control group and for the main group, like for the hoppers?
Well, about the first question, for instance, for estimating the support, that is the first problem that I mentioned here in the Euclidean space, there are some options if there are dependence. But in the case of highest density region, I don't think so. And about the second question, in this paper, if I understand well, we use distances between sets to measure the difference between two populations. So if you have the highest density region of sandhoppers in April and the highest density region of sandhoppers in October, you can calculate, for instance, the house door distance between these two sets, these two regions, and you can know how different they are. Different they are. Okay.
Yeah, that's nice.
But maybe nice you can search another error criteria, of course.
Yeah, okay, yeah, that's nice. Thank you.
All right, who else wants to go ahead with questions?
I just had a question / curiosity, if I may call it like that. Well, first of all, very much thankful for your presentation. I think it was really nice. Good work. So I was wondering on the forthcoming part, actually. I mean, what was the? I don't know. I'm not so sure if you're working on that right now, but if so, what are the main, let's say, technical limitations that forbids to extend the presumed consistency in the Euclidean setting to the directional case, if they are?
Well, we think that we have the proof, but no limitations to extend the proof. No, the proof is quite similar in the Euclidean space. Maybe it's quite simple.
Okay, thanks.
Okay. Other comments, suggestions, questions? I was wondering about one thing. So when you showed your graphs in the beginning, I was immediately thinking about the excess of mass methodology,
Yeah.
or as Jose was doing the bump hunting.
Yeah.
Because I know that for some time this was Rosa's directional life, to go for excess of mass. So I was actually wondering why. So you said there we did not go for these types of methodologies.
Yeah,
I was actually wondering just why, given that Rosa has spent this time on that.
Yes, this is my first work in the directional setting. So this is the first step. But of course, the another methodologies that I told you, we think that they could be extended to the directional setting.
Okay, so this is in plan. Okay, that was not clear. I thought it was just have been put aside. Okay, good. Thank you.
Thank you.
So, if
Christopher, just a short comment on applications, let's say. I think this earthquake story can be easily moved to the COVID right now.
Use sorry,
Yeah.
I have a recent paper on COVID, but in the Euclidean space. I use the geographical coordinates latitude and longitude, and I will estimate the highest density region, but in the Euclidean space.
So it shouldn't be difficult for you to move to the directional, to the sphere.
No.
Yeah, I think
no.
it would be great.
No.
Really, really great.
No.
Thank you.
Thank you.
good, so then I think we can thank the speaker again. So.
Okay, thank you.
And yes, we move on to the second speaker, which is Najme Nakai-Rat from the University of Pretoria.
Hi, Prof. How are you? Hi, everyone.
Hi, everyone. You want this recorded?
No, thank you.
Okay, then